Friday night, time for an evidence-based triathlete podcast. Hey, Ted, how's it going?
Friday night Super Bowl weekend in Las Vegas. Man, I
Yeah,
tell you about words I never thought I'd say about 10 years ago about Las Vegas, having the Super Bowl in Las Vegas. Oh my gosh, it's been a
I
crazy.
know.
yeah, unreal. And we've got our special guest, our local expert in cycling and all things wheels, Jon Thornham from Flow Cycling. Hey, John.
Hey, how you guys doing? Happy to jump on. This is always
Yeah,
always fun to do.
Yep.
awesome. Well, thanks for jumping on. And those who just were on Facebook Live and caught some of the pre-show, we were talking about Ted being winged, and we're going to have to go in and cut his bicep tendon
But,
next. So,
it's so funny you said that. So I have a sling on for our guests that follow the injuries of Ted. Um, it's been a rough year. So I got a PRP injection in my bicep, and John was like, "Hey, my dog just got one of those," and um, he said there was either that or cut the bicep tendon. And John, you want to know the truth of the matter is that's the next step. If this is
yeah,
for me
Oh,
is the
well, I
exercise.
don't like the sounds of that.
Yeah, and I don't either. So I'm like, that's why I went this route first, because the sound of like, yeah, you don't, and he's like, you don't really need your bicep to swim, like the
hmm
long
Yep.
bicep, right? So I'm like, well, if that's what it's got to be, I mean, because I'm a crazy triathlete, I'm like, or I could just not swim and I could just
hmm
everything would be fine. But you know how
Yeah.
it is. We're athletes, and this is what you got to do.
No duathlon for Ted. I don't see
yeah.
that happening.
I've done a few. They're not nearly as much fun, and I don't even really like swimming. Triathlons are so much more fun.
Well, you love biking, and this is going to be a great podcast episode to talk about all things biking. And really, John and I were talking about topic, and he has some really great ideas and thoughts and information on cycling efficiency. So I guess we didn't even decide where we wanted to start. John, did you want to just go into a little bit of talk on
Sure.
cycling efficiency?
Maybe
Yeah, I mean, I think, yeah,
John, sorry. Let's just start off where we were just off air there just a minute ago, talking about like, literally cycling efficiency the way you were already describing it, because that was so.
yeah.
So go ahead.
No, I think, what's interesting is I've been doing this for going on 15 years, and we do a lot of R&D, and you know, I don't know why it just hit me, but it feels like when you think about cycling efficiency, it's been something that's been on my mind a lot lately. And I think there are so many individual components when it comes to cycling that it kind of gets confusing. There's aerodynamics, there's rolling resistance, there's the rider, there's all these different things. But really it sort of breaks down to just one simple equation. Ultimately, what you want is you want the power that you're putting into the pedals, you want that to move you forward. And so if you think of an equation, cycling efficiency is really the input power of the rider, and that has its limitations. So you can train yourself as much as possible. You can get yourself as fit as possible, and that's going to give you a certain output power or input power. And then on the other side of the equation, you have your output power and minus your mechanical losses, right? So what that means is, sorry, I flipped that backwards. The output power is your forward motion. So that's on one side of the equation. The input power is on the other side with the mechanical losses. So what you ultimately want to do is you want to minimize those mechanical losses, because we know on the input side, the only thing that you can do is you can only get yourself trained to such a fitness level. So if you're progressing in your career as an endurance athlete, then you are going to hit limitations as you're training, right? So Ted's been an athlete, John have been athletes for years, and so they've been able to work themselves more to get more and more input power and be more and more efficient on that side. What most people don't necessarily think of is the mechanical side. Like I said, it comes down to aerodynamics. It comes down to tire pressure and rolling resistance and all these other things that we can adjust. I've been to Kona many, many times. I've walked through the pro bike field every single time. And what I do know is that every one of the pros, they do take advantage of every single mechanical advantage they can get. At least the guys that are winning do. I was in Kona back in 2016 after I just did a giant tire study with rolling resistance. And I realized one of the guys that came in top 10, a very well-known triathlete in the space, American, he lost by 7 minutes, and he chose a tire in Kona that year that lost him 8 minutes just by that tire selection.
Mm.
So when you looked at the other guys in the field that year, though, there were specific choices. Now, he likely would have won the race or been very close to winning the race had he chosen a different tire. So it's exactly what I mean. It's this whole balance about making sure that your output power is efficient as possible, because any watts that you put into the pedal, you really want those moving you forward. You don't want them wasted into any sort of losses on the bike.
Yeah, and we work super hard to gain, like, to raise a rider's FTP 10 watts
Yeah.
takes a lot of, especially when you've been training a long time, right? Like if you've been a habitual trainer for 5 years or 10 years and let's say your FTP is 250, to go to 260 for that person is a big investment of time and effort and energy, but they could easily lose 10 watts on tire choice, like or tire pressure. I mean, we did a lot of tire pressure stuff with you. Easy 10 watts on tire pressure if it's wrong.
It is. And what I find so interesting that you're saying is you can take years. It can take so many hours of dedicated focused training to just eke out these watts, especially as you're getting more fit and more fit and more fit. And sometimes these mechanical things that you can adjust can give you 10, 15 watts just by making simple changes. And it's almost like those are somewhat ignored. So what I like to do is like I say, I try to make it as simple as possible, where if you think of anything mechanical, aerodynamics, rolling resistance, and we'll talk more about them in a few minutes, but like you just got to group those into sort of one section that you're kind of managing all of that as one thing. And those as a whole, you want to just have that number of watts that are being consumed by that to continue to go down and keep trimming those away as you progress on the mechanical side of things. That's how I like to see it. And it really allows people to focus on it's me and and the bike, and that's how I'm going to get my speed. It's like no different if John and I go for a ride, and I know we don't have the same FTP, but if we did, we're both putting out 250 watts, and John's been smart and he's taken every single mechanical advantage he can. At the same output power, he's just going to be faster because I've ignored these things, right? So we've trained the same, we've got the same program, we got the same coach, we got everything else, but he's going to walk away from me because he's been smart on the mechanical side.
Which probably isn't the case, but so I know you're super into the fitness side of generating power, but even more so on the mechanical side. And I love the equation. Just looking at these input powers and output powers. Can maybe just give everyone sort of a brief overview of the type of testing you've done, because these aren't things that you just sort of pulled from your hat. I mean, these are things that you've
No.
actually looked at and done projects on.
Yep. I mean, the first thing that I would say that we really focused on was when we first started the company back in like 2011, 2012 was aerodynamics. I mean, cycling back then was really primarily focused on aerodynamics. There wasn't a lot of stuff going on with rolling resistance back then at all, tire selection, tire pressure, any of that sort of stuff. So the primary focus in the beginning for us was aerodynamics. We started off using computational fluid dynamics software, which we use because it allowed us to do a lot of testing as opposed to going to a wind tunnel. But shortly after we developed the first generation of wheels, what I noticed was there wasn't really anything that was related to what a cyclist actually experienced. And what I mean by that is people would come up with a rim shape, they would put it into like a CFD software, they would put it into a wind tunnel, they would sweep it over a series of angles, and then they get this graph. So you see basically how it performs. When you have low drag, that's great. But what people were doing is they were just looking for a low spot on this graph. And ultimately, what I thought was, well, what does that matter? I mean, we can't pick the yaw angle that we ride at. We are only subject to the yaw angle that Mother Nature gives us on the given day. So from there, I built this computer. It mounted to the front of a bike. And what it was doing is when we rode it over a number of different Ironman courses. We rode it on near the coast. We rode it through in packs or groups. We rode it through trees everywhere. We can hills everywhere to get as much data as humanly possible. And what it collected relative velocity, which is really what aerodynamics is based on. Many people think that aerodynamics is based on your speed. It's really not. I mean, if you're going 10 miles an hour and you've got a 10-mile-an-hour tailwind, you're really in zero relative velocity. There's no airflow around you. It's like when you ride and you're in that perfect spot and everything feels silent. So if you were riding 10 miles an hour and you had a 10-mile-an-hour headwind, though, that would be a 20 mile. You got to add the two and the other two subtract. So once you figure out what that relative velocity is, and we measured that on the bike, and then we measured that the angle that the wind hit us at. So right in your face would be 0, and off to the right side would be like positive angles, and then off to the left side maybe negative angles. So as we collected all that data, what we then did is I developed this optimization algorithm that we use in computational fluid dynamics software. And we then gave it a parameter set, which basically says you can design a rim shape within this box and around these parameters. And then what it did was it iterated over hundreds and hundreds of shapes to basically come up with the fastest shape that met that data that we collected on the road. So it was really the first time that anything like that had been done. And it just proved to develop these incredibly fast wheels. And we coined a term back then called net drag reduction value. So we look at a summation of the angles all across what the rider experiences. And then we use that to give a speed. So we didn't just go, hey, we found this rim shape with a really great yaw drag at 17.6 degrees of yaw, which nobody ever experiences. And it's the fastest wheel. That didn't make any sense, right? So we designed wheels that fit in that box. After we developed that, the next thing that we moved to was we went to the wind tunnel, and I was honestly in the wind tunnel thinking, I don't know how I'm going to design a faster set of wheels. And then what happened was we were doing this big giant tire study to study the aerodynamics of all these different tires. And we looked at tire pressure, tire treads, and a whole number of different things and how they interacted with the wheels. And a good friend of mine reached out to me and just said, hey, I'm doing this starting this rolling resistance thing, and I'm doing a lot of testing. And he said, can I get all those tires and we'll compare the two. I honestly thought that it wasn't going to matter, completely naive, ignorant to it. And he sent the data back, and I was just blown away. I mean, it's easily half the watt loss or savings when you look at rolling resistance. And so it really made me think about how we would design wheels moving forward. That's when we teamed up with you guys at UNLV, and we really needed to figure out how to measure rolling resistance on the road, because we did all our other stuff on the road and we don't want to do it in the lab. The big reason you don't want to do it in a lab is because steel rollers are so smooth that you don't get the natural frequencies and resonance that you get from a vibration perspective from the road. And so we developed that system where we were able to measure rolling resistance, and we proved that a wider internal rim width allowed us to lower the rolling resistance for wheels. Then we optimized a tire around that unique rim shape with a super wide internal, which then led to that. Finally, the most recent thing that we've been really working on is the concept of vibration. Vibration, we've learned everything that you can imagine has what's called a natural frequency. So the natural frequency, the best way I like to describe it is it's almost like, in some capacity, it's almost like a trampoline. When you're jumping on a trampoline and you're bouncing and you're in rhythm with the trampoline, you kind of have this natural bounce. If you get out of sync of that bounce for any reason, you don't bounce. Natural frequency is very similar, and what I mean by that is if the vibration or the frequencies around a certain body are activated in that right frequency range, the energy just really starts to oscillate back and forth, and so you get this really dynamic sort of motion. A good friend of mine, we did some natural frequency vibration testing with wheels, and then we started to look at what tire pressures and how they responded to how the vibration in the wheel responded to different tire pressures. We've known for years that there's a thing called an impedance breakpoint. So in a lab, if you're on smooth rollers and your rolling resistance is at a certain number, as you increase the tire pressure, that rolling resistance goes down. On the road, that's not the case, because eventually you get to a point where you hit this impedance breakpoint and your rolling resistance spikes very, very, very quickly. As a result of that, we wanted to study, is that related to the natural frequency of the wheel, and is there anything in there? And we found out that is. So that's a very quick crash course of like the things that we've studied R&D wise. But yeah, go ahead and ask any questions you have.
No, that's awesome. I mean, it's pretty amazing the work that you're doing and all this type of testing and really diving in deep. I don't know how you run a company and do all that at the same time.
Well, we got good partners like UNLV.
No, I've loved the work that we've been involved with you, and I've learned a ton, especially about the vibration part and the tire pressures and how much my thumbs can hold up on changing tires. That's
Yeah.
that's
Yeah,
great. So go ahead, Ted.
when we started working with you, it was obviously super fun for us as well. And I kind of thought of it as like, John and I were cheating the system because we were learning before our competitors, right?
Yeah.
And now everybody knows this stuff.
Yeah.
Like, we were some of the first people to be rolling low pressures on wider range, right?
Totally.
And we're like, oh man, like nobody else knows this. I want everyone in the pit, in the transition hey, 110 is what you want. And John and I are rolling at 85.
Mm-hmm.
Yep.
And I'm like, I don't
With
want
like 28s, right?
and I don't want anyone to know, but now everybody
No.
knows. And I'm like, oh man, we got to find something else. So hopefully vibration is the next thing. And John and I, oh shoot, we're on a podcast. People are going to know. Never mind.
Yeah.
The end of podcast, mic drop, we're done. But seriously, what could like we do, not in research, but just like the age group triathlete. If we know this wider is generally better, lower pressures in general are better. When we look at something like vibration, is there something like an age group triathlete could do to optimize that at this time, or is this a future thing?
I think it's going to be a future thing. Honestly, you need sensors in a wheel to basically understand the vibration pattern. We've been looking at sensors in wheels for that. It's not ready at this time, but what I can tell you is that we have done a lot of research on tire pressures that are optimal for athletes. The biggest thing that we've really been pushing lately is making sure that the tire pressure that you're putting in your tires is actually accurate. And this is something that every triathlete can do, right? So if you think of a standard floor pump, you're looking at a plus or minus 9 psi of what the gauge reads. So if your gauge says, let's say you go to our charts, you realize for your road surface condition, your tire and all that sort of stuff, your optimal tire pressure is 85 psi. Well, you pump up to 85 psi and you're looking at the gauge, it could be 94 psi, or it could be 76 psi, right? That's that plus or minus. The biggest thing that most people don't realize is that for every watt that you're over, or sorry, every psi that you're over, you're losing 1 watt. So if you're supposed to be at 85, but you're at 95, you just blew away 9 watts, right? And that's, like you say, when you think about training in FTP, so your pump really, really matters, which is why we developed this product. Actually, John was talking about this product. We talked through this, and then I went out and I kind of ran with his idea, and we developed this thing called the flow air gauge, which is an incredibly accurate pump gauge that connects to any pump. Most pumps that you're going to find with the accuracy of like this plus or minus 1% span. So basically it's 120 PSI pump. So you're at most, you're going to be like 1.2 PSI over. That's at full span. So if you think that, when you think about that, that's, ideally losing like a watt. You can even go under 1 PSI, which you're recommending. You're guaranteed not to lose any watts. What's great about this product though, is when you think about most pumps with this accuracy, it's a full floor pump, right? And they're super expensive. You're talking $400 or $500 for one of these pumps. When you're trying to travel with that too, it's very difficult to travel. It's a pain to travel with. The air gauge is something that just basically connects to any pump. You can use a mini pump. You can use any old transition pump that we probably know is worse than plus or minus 9 PSI. And you just read the gauge. It's super cool. We ended up designing this really cool chuck too that locks in pressure. It's easy to remove. Just a fun project. But I think that right there is something that most people could think about. While we're not there on vibration yet, there are really great charts and there are ways to manage that tire pressure really effectively and just save yourself a ton of watts.
Just to follow up on that, and you mentioned it, what about road surface, right? So if I'm doing a triathlon, and I'm just thinking, I don't know how familiar you are with some of the road surfaces. You've been to Oceanside, I think.
Yeah.
Okay. So
Oceanside's brutal.
Brutal, right? We've got some sections that are really nice, smooth pavement. We've got some sections that are concrete. We got some sections that are pseudo good. How do I decide on those charts, because road surface is important, right? How do I decide what to do?
So I actually went out last year. I did some projects. I went out and previewed some courses and talked a lot about this. And one of the things we also see is we also look at it from a gravel perspective, right? Because in gravel races, like one of the ones I did out in for the Belgian waffle ride, is some of those years you can have 80% pavement and then you go into some gravel sections, right? And I almost look at a lot of race courses in Ironman can be very similar. Like when you look, you go out to Oceanside, and as soon as you hit that section of the old deserted, like abandoned highway, that thing's rough, right? I mean, it's real rough. Ultimately, the higher your tire pressure on our graphs, it relates to a smoother road surface, right? So, and the reason for that is if you think of the road surface, most people think it's flat, but it's really not. If you get down and really look at it, there's all these little bumps. And so when your tire pressure gets too high, what happens is your tire actually starts to bounce up and down over those bumps. And anytime that the bike or you are going up and down, it requires energy, right? And the only energy source that's going into that bike is the power you're putting into the pedals, right back to what I was talking about, input power. So as a mechanical loss, you're actually losing energy by bouncing up and down as opposed to using that energy to push you forward. So when we have a rougher road surface, we lower that tire pressure. What I like to do when I know that there's rougher or varied surfaces on a course, I try to like to think about it as what percentage is each one broken up into.
Mhm.
If I know that over 112 miles, I've got maybe 5 miles of really rough section, don't really worry about it all that much, right? It's like less than 5%. I'm not really worried about it. But if I get to a section where I'm starting to get into 30, 40, 50% of like really rough sections, I'm adjusting my tire pressure lower because again, you're much better to be under pressured than over pressured. When I say that you lose 1 watt for every PSI that you're over, you do not lose 1 watt for every PSI that you're under. So you're better to be under. So in a situation where you have a varied road surface, I like to look at the percentage, and then based on the percentage, I kind of go with the worst case and how that all works out, and then I veer to the lower pressure to make sure that I'm not losing watts when I get to that rough section.
I love it. In fact, I know you did the video on Oceanside and you talked about this and you gave a recommendation for people on tire pressure for Oceanside. I think you
Yeah,
did that for Kona as well, right? Is
I
that,
did.
yeah.
Yep.
And
Yeah, I
that's
was
got,
out there last year for something, and I went and I just it was funny. I drove all the way up to Javi and I looked at it and I talked a lot about different stuff up there, and it's so funny. It just total side note, but the day that I did get up to Javi, people talk about why discs aren't legal there, and everyone always thinks that the wind blows across the road, and it doesn't, right? We've studied this, like I said, we've got over hundreds of thousands of metrics of looking at this. But the day that I was up there was funny because the video footage, there's trees on the side, and they were literally blowing straight across the road. I mean, it is just one of those crazy wind situations where it comes and it was blowing, towards the ocean. So it is brutal out there. But that course is also very known for the steel belted radial and stuff that's on the course, right? So those are again all things that you need to think about. But that is a varied surface as well. But it's pretty consistent. The town is pretty good. But I drove the whole course and it's pretty consistent compared to something like an Oceanside.
so one of the questions we got from one of our members before when we posted we're going to have you on is about where to ride on the road even. So you can choose, different sections of the road, or maybe, most people will stay, yeah, obviously to the right, but you still have quite a bit of room to move around on the road, and some parts may be smoother and some parts may be rougher. How do you factor
Well,
that
avoid
in?
the rumble strip at all costs. If there's a rumble
Yeah, yeah.
strip, that's not going to help anybody. It might be fun for a minute, but that maybe
Yeah.
a minute only. Um, to be honest, that's a great question. I would veer for the smooth stuff, but this goes back to like when I talk about wheel selection.
Mhm.
Sometimes I think that wheel selection really comes down to how somebody mentally is thinking about their gear and thinking about things, right? So I always like to say that you want to be on the deepest wheel you can handle. And most people, that's kind of a thing when you talk about like road racing or triathlon and what they generally mean by that is, can you handle it physically? I also like to include the mental aspect of that. Because if I put myself on a front wheel that I know is deep and maybe I can handle it physically, but if I'm riding in a race and mentally I'm thinking the whole time, is that next gust of wind coming? I think I can do this. I think I can do this. What happens is you start to, I think it's somatic. It's like a somatic system that basically you're increasing your heart rate because you're starting to worry about the gear that you're on,
Mhm.
right? And obviously, what we want to do when we're riding is we want to have like a lower heart rate. We want to have we want to have everything as chill as possible because we're trying to use that again output power to put power into the pedals, not wasted through worries. So I think the same thing goes for when you're riding. Um, if you're honestly trying to like track where you're going every single minute, I don't think you're focusing on what you're actually out there to do.
Good point.
So I would probably actually a lot of times like the paint,
Hmm.
like if you can ride on a line, It's very easy to stay on a line, but if you actually get down and look at the paint, what I notice about the paint, as long as it's not wet, don't ride on it when it's wet. The paint almost fills some of those grooves, some of the like the imperfections in the road surface. It's almost like a filler. So if you can actually ride on a line, in a lot of situations, you're getting a smoother road surface than the other stuff. So, as long as you're not running into or it's in the course, I would ride on the paint because it just gives a smoother surface and it reduces vibration.
Okay, you're giving away all my tricks. Do now. Seriously, I always ride the paint. Always. Okay, and the other thing I'm gonna add on this, especially in a race, I want to be more left, like legally, because I read somewhere, and this could be BS, but less chance of getting a flat because more debris potentially from the
Oh, that's
if it was raining or wind or whatever could. So they said like even if you can get a foot more to the left than closer to where the gravel and stuff is, it might be better.
Oh, yeah.
Less chance of a flat. And to me, that's a big thing when I'm racing. Like a flat is obviously the last thing you want to have happen. And so
Yeah,
if all else was equal, go just a little bit more to the left.
definitely. Because I mean, you just look at it, roads are graded, right? So gravity, you get wind, you got rain, you got things flipping off cars. And as that naturally settles, it wants to take that gravity path down to the lowest point, right? So yeah, if you can get away from any of that junk, I mean, there is like some people look at on certain roads, there's like a concrete buffer, arguably concrete could be smoother, but the junk in there, I would just stay clear away from that. I mean, even if you are riding tubeless, which helps so much, just going over that stuff, I just think is messy. Plus, concrete always has saw cuts, right? So concrete, if you start to get these like, if it's new and it's new concrete, the saw cuts you don't really notice. But when you start to get older or aged concrete, especially when you get anywhere with a freeze thaw cycle, you get those bumps, you get those heaves, and those every time you impact one of those, I mean, you're just kissing watts away at that point. You're just kissing them goodbye. So I would stay away from that. But again, paint. I like paint.
How about it's funny, actually, we've never talked about the influence of rain on tire pressure. So, a lot of times I stand in transition, it's raining, and the announcer will start saying, well, drop your tire pressure by 10 PSI or something like that. Have you thought about rain influence at all or wet surfaces in general?
Sure. I mean, ultimately, when you think about what people are the standard, which was for years and years and years, was 120, right? So what we do know is when you look at vibration when a cyclist is riding, and one of the big things that we've picked up a lot of this from was gravel. So when we released the gravel line, a lot of people before like I'm just going to show you something. I know a lot of people may not see this, but it's kind of cool if you can see it. This is a rim profile, right?
Mm-hmm.
And so it's cut, it's a section. And so on a wheel, what you get is you get this sidewall down here. And if you look at it, it's flexible, right? And so in gravel, what was happening is you had these guys with like box section rims, and as they're going over certain gravel and imperfections, their front wheel chattered and it would kind of drift left, right, left, right, left, right, left, right. Well, when you have a wheel that's like this and you have this sidewall, and if the carbon layup is designed properly, then what happens is a lot of that vibration is absorbed in this sidewall of the wheel, right, of the rim. And this acts as a leaf spring. We have like a leaf spring on a vehicle or anything like that. It absorbs that vibration. So what people were reporting back from the gravel stuff, which is great because you got what we want, is that they feel that they have better tracking and they have better traction. So anytime vibration is introduced into a system, you have three axes. You have, if you think about your fingers, you have like X maybe forward, Y maybe left and right, and Z would be up and down. So when you excite something with vibration, all of those axes generally get excited. And so there's energy moving, oscillating back and forth in those directions. When you think of the Z direction, which is up and down, when you get that sort of vibration, well, what happens is you get these small weighting and unweightings of the tire on the road surface. And so when you have a tire pressure that's too high and you do start hitting those natural frequencies and you're over that impedance breakpoint, when you're making a corner, what happens is that wheel is actually sort of skipping down the road. When you lower tire pressure, right, you eliminate most of that those oscillations in the wheel. You're avoiding the natural frequency of the wheel, the harmonics of that wheel. And so what happens is you get rid of that up and down motion. So as you corner, you get better grip, you get better traction, you get a whole number of different things. The reason a lot of people talk about lowering tire pressure in the rain is because naturally rain, it creates a slicker road surface. If you've had any oil or any fills from the tires or from vehicles, it just makes it super slick in the rain. So if most people adhere to the proper tire pressures that they need to go with, the announcer probably wouldn't need to say lower your tire pressure 10 psi. But I think it's because they're coming from that holdover of 120. You're just going down. It's like if you've ever ridden a mountain bike and you're in the go try to take a corner, your tire pressure's too high, you learn real quick to ride lower pressures. Just how it works.
Okay, I want to talk about some tires. So
yeah,
first things first. When we talk about tires, I'm not going to ask you what the best tire is, okay? Because we're saving that for after we turn the podcast off, and you're just going to. But in all seriousness, there's this conversation that's had about like aerodynamics of tires and rolling resistance of tires. Okay, so to me, those are like the two things I want to think about, right? Like once we get the tire pressure right, those are the two things. So what's more important, or are they both equally important? Aerodynamic or rolling resistance?
I'm going to throw a third one at you. And I always describe tires as a three-legged stool, right?
Yep.
In a three-legged stool, if you lose one of the legs, the stool falls over, stool is useless.
Yep.
I almost think of tires in the same capacity. And those three things that I want to think about are aerodynamics, rolling resistance, and durability.
Yep.
Right?
For sure.
Aerodynamics matters because if I have an aero peg, well, it's just I'm losing watts. Rolling resistance is the same thing. It's like the tire I talked about in the beginning when I was talking about with that pro athlete. And then sometimes you get these tires that just have such great rolling resistance, but their durability is so terrible. They flat. And if you have to stop, change a flat, I don't care how many watts you're saving. You've lost more time in the change. And there are tires that are notorious that are great rolling resistance, but they're just terrible durability, right? They tear easy, they cut easy, and they're a pain to work with. So I don't think necessarily any one of them is most important. I think the combination of the three of them, is what is important. And so you need to have a balance of those three things, right? If you don't have that balance, I just think like the stool, it starts to fall over, you lose one of the legs. And I think that's the support structure you need from a really good tire.
Yeah, so you're literally triangulating, you're trying to get the best out of all three. But you'll never you'll never have the best rolling resistance and the best aerodynamics and the best durability. Those things cannot exist.
Two are really sort of connected really well, right? So the two that are connected is really the durability piece and the rolling resistance. The aerodynamics is kind of off on its own.
Yeah.
I could have the best aerodynamics and then I could design other things because really the aerodynamics is about the tread pattern, not the tread compound, right? So those are different components.
Right.
The reason that the rolling resistance and the durability are connected is because if you look at like track stuff where guys break records, some of them use like these silk sew-ups, right? They're so great from a rolling resistance perspective, but if they're not on a wood track, I mean, they would just disintegrate, right? Yeah. So the tread compound and how the tread plies and everything are created and what that internal structure is really impacts your rolling resistance. So it's finding that balance. The rubbers are also important in it, but finding the right construction to sort of balance those two. How do we make sure that we have really good low rolling resistance? And how do we also make sure that we have something that is durable enough that it's not going to flat?
I think there's one other piece of tires that I want to throw at you, and maybe this is just me, but I've found some tires that actually I feel better on. Mm-hmm. Like maybe it's the sidewall, the casing, or something. I can tell it's just a better ride. Like I wouldn't necessarily race in them, but like for my road bike, like just cruising around, like this feels better than this. Mm-hmm. Have you come across?
Yeah, so it's interesting. It reminds me of this study that I've read and I talk about it all the time. It goes right back to why people believe that higher tire pressures feel faster. right? So there was a study, I think it was Germany that this study was done. They took subjects and they put them in a car and they blindfolded them and they said, what we want you to do is tell us which road that we drive on is the roughest surface. And so they took them down 3 roads, which they didn't know, but it was the same road every single time. And what they did is they increased the speed of the vehicle from 70 kilometers to 80 kilometers to 90 kilometers. And in every case, everybody said the 90-kilometer-hour speed or road was the roughest. The reason for that is because it creates a higher vibration. And what the body perceives as fast is vibration, right? When you naturally lower your tire pressure from 120 psi, well, you reduce the vibration. So when most people go out and they ride at like 85 psi for the first time, they just feel slow. But I always equate it to like if you've ever had a really old car, most people have had an old car, beater car in college at some point, and you drive that thing 100 miles an hour, which most college kids do, you feel like you're going to die. And then when you get older and you buy a nice car and it handles really well, you can go 100 miles an hour and you feel like you're going 60. Again, the reduction in vibration that goes through the frame, the body, and ultimately you sitting in the seat gives you a different perception. I would almost wonder if the plies of the tire and what you're getting, you're perceiving as a more, and this is really subjective. Does it feel better because it feels smoother? Does it feel better because it feels faster? What people would perceive as what feels better would really be sort of related to the individual. If I were to ask you specifically, does this tire feel more comfortable than the other one? Does it have more grip? Is it smoother?
Yeah.
Yeah. So yeah, I honestly think that that's probably related to the vibration.
Yeah. And in a good way, right? Like if it feels smoother, it should be less vibration and the harmonics and all this. It actually can do with my weight on that tire too, right? And my bike's weight and all of that. It might feel better for me, but I put somebody that's 200 pounds on it, it might not feel better
Could be totally different
for them. It's kind of like, John and I, we talk a lot about shoes, and like the right shoe is the one that feels good for you, right? It doesn't matter how fast Kipchoge is, and if it doesn't feel good for you, it's not
doesn't work.
So I think there's a piece, there's a piece of just feel that also like it matters when you're on the bike.
Well, the work we've been doing with even compression gear, it is getting more established now that the belief in the product actually does influence the outcome of the study. So it may even be something like you believe that these tires are faster. I don't know if it's been tested in cycling, but that goes right along the psychology aspect of performance. But that being said, and I think this is tied to it. How about front versus rear wheel and your choices that you may make for tire or even tire pressure on front versus rear, and even aerodynamics of the tire wheel?
It's funny you bring this up, and I've had this question asked to me a lot, and there's been this theory out there that the front wheel needs to have a smaller tire than the rear wheel.
Mm-hmm.
And I'm just going to say that we look at the fastest tire, but it doesn't matter if it's on the front or the back, right? Like if we look at a combination of aerodynamics and rolling resistance, even though the front wheel does experience probably more of an aerodynamic, it experiences a different aerodynamic impact. You're getting more, if we want to call it laminar flow, off the front wheel. And by the time the air moves through you, your legs, and the back, we have more probably a turbulent flow depending on the yaw angle. Laminar means smooth flow for people that are wondering what I'm talking about. Turbulent basically means like chopped up. If you think about it from like a river, you see a river moving down and everything's very smooth, there's no rapids, that would be like good laminar flow. The minute you start to get around a bunch of rocks and things start to get all sort of chopped up and you see that like visual chop in the water, that would be like turbulent airflow. So there still is an aerodynamic impact, and arguably there's more of an importance on the rear wheel for better aerodynamics because you want the air to reattach to the wheel. If we don't have good laminar flow or we don't have attachment around a tire and a rim profile, then we just lose all of the aerodynamic benefits of that wheel, right? So that's why if you've ever looked at a wheel in a wind tunnel, we generally do sweeps of yaw angles. So if you start at 0 and you go and you open that yaw angle and you just keep opening and opening and opening, well, the air starts attached on both sides very smoothly. And let's say that it detaches at, I don't know, 15 degrees of yaw. And if you sweep all the way to 20 and you go back, most people think that the air will reattach at 15 degrees, but it doesn't, because it is easier to keep air attached than it is to reattach air. So normally you get reattachment within 2 to 3 degrees of where it detaches, but less. So when you have and that's when the air flows is turbulent. There's a lot of things happening there. So when you think of air coming through the legs or around the frame, you want a really good aerodynamic transition and in your best attempts to sort of recapture airflow and to get it moving around the rim in the best way that you can. Again, this is a lot of what we did with gravel. Most people believe that you can't have an aero gravel wheel. There's some stuff out there that people are claiming it's aero at like 40 mils. I just don't know how that's possible. When you're coming around a big tire like that, you need some width and you need some depth in order to sort of recapture that stuff on the backside. So we're at 55, which is super deep for a gravel wheel, but there are being designed that way, you save the same amount that on a gravel set from a watts perspective than you do on a road set, which is kind of mind-boggling when you really think about it. But yeah, so long answer to your question, but if you're gonna you can get away with a 28 mil tire and that's optimized for your wheel, use the same on both. The only thing you may want to consider is slightly different tire pressures based on the weight distribution of how it is. But for triathletes, for the most part, it's pretty much known to almost be like a 50-50 split. So you would use the same pressures.
So I love this talk, and we don't talk much about gravel here because, quite frankly, John and I don't ride gravel.
Yeah.
Why not like a 90 mil? Like, what's the downside? Because it seems to me that there would be, you're going slower, so there's less wind coming across. So like, what's the hesitancy to going even deeper, like an actual triathlon wheel?
Two things, really. One thing you have to consider is that a lot of times in gravel, you do get a lot of like mud.
Oh, okay.
Right?
Caked on.
So when you get too deep, you're basically carrying around a lead balloon. Oh, I got some balloons going. You're carrying around like a lead wheel, you know? So if you get caked on like a 90 mil profile, like that's just wild.
Okay.
The other thing is though, like if you look at our latest generation of wheels, we went from a 95 mil wheel to a 77 mil wheel. And the big reason for that is two things. It's actually faster than the old 90 millimeter wheel. And the reason for that is because we were able to make things much wider.
Yep.
And so I've been talking for years now about the concept that aerodynamics is not just depth. It's a combination of width and depth, right? There used to be this old thing. Oh, it's still relevant. It's called the rule of 105. A lot of people talk about the rule of 105, which basically talks about the ratio of your tire and your rim profile, and it's 105%. I'm not saying that I know the guy that developed that, and it was brilliant at the time for him to come up with it, and I think it's a great thing, but it was really based around aerodynamics, right? And aerodynamics alone. But now that we know that rolling resistance is also as important, we are close to the rule of 105, but we actually break it because when you add in the rolling resistance component, those two add together, the aero watts and the rolling resistance watts, and you get a faster combination, if that makes sense. So we're close to 105, but we're within like 1 or 2 points of it. But the wider tire just eliminates those losses that you would break from the 105.
So the question that we were going down the path is what can we do? And this is all related and great. How about even with the width that you're talking about and the tires or the wheel structure? How about spokes? Number of spokes, shape of spokes.
We've looked at spokes, like we've actually studied round spokes versus arrow spokes. They do make a difference. I mean, it is like it's within a minute, but a minute is a minute. I think I have this like sort of frustration with the way some things are going in cycling. Everything is moving to disc brake, and am still a believer that rim brakes are faster. They just are, and I'm not really sure it's really needed for a triathlon. And I know it's being pushed by the bike manufacturers, but one of the things that you have to take into consideration when you run a disc brake bike is you can't use a radially spoked wheel in the front.
Hmm.
You can't brake from the hub when you don't use a cross, right? So it immediately requires us to go up to 24 spokes, and we have to use a 2 cross on both sides, which adds minimal weight, but it adds weight, but it also adds more spokes. And that's just not faster, and I get frustrated by that. I know as much as I know that a rim brake bike is faster, if you told me today that I need to go buy like a brand new tri bike, because I know everything is essentially going to disc, it would be hard from a almost like a financial or like longevity perspective to really think of rim. But if you can get away with it, I mean, you look at a brake like the tri-rig brake, the Omega, you look at like what those guys have done over there, some of the integrated stuff, it's just faster. I mean, anytime you put, I mean, aerodynamics is all about like making smooth flow around things. And then you just take this big honking caliper and rotor and you just stick it on the side of something and you think, I mean, it's just, I don't know how people think that's going to be, it's just not faster. We've noticed when we compare our rim brake wheels to our disc brake wheels, it's 2 watts, right?
Hmm.
Just because of putting a brake on there. And those watts are, when you look at input power, they're hard to come by.
So
Rim brake in
how
front.
that's number 3 that you've ruined for me, by the way. I literally built a brand new bike last winter that was, I had to hunt down to find a rim brake, high-end rim brake bike, because you can't buy like a high-end rim brake bike anymore. So
Hmm.
I get the last generation you could possibly get of the Argon 18, which I was on before.
Yep.
And man, it is so freaking buttery, lightning fast, right?
Yeah.
And I am so happy when I'm passing people and they're on the disc brake bikes and they got the caliper sticking out, and I'm just like, I got none of that. And because my brakes are all integrated in, it's so smooth. And like I said, no one even thinks about the spokes, right?
Nope.
And that's a big deal. Like 2 watts, or spokes might be even more than 2 watts. Having that we were talking about the cross pattern and stuff like that, and that doesn't even enter into it. And I know these manufacturers are pushing it, but I'm with you. A rim brake bike on a triathlon bike is faster.
Yeah. I mean, ultimately I mean, if we had our ideal situation, every molecule of air that went over your bike would be laminar every given minute, right? And so when you start adding things in there and you're adding these complex spoke patterns and those things are rotating at however many revolutions per minute, it's a blender. You're just chopping it up, and we try our best to reduce that.
Yeah. And the manufacturers come out, well, the frame shape is so much faster, and like, okay, great, but if the front of the bike is not right, the frame might be faster.
But that's a very interesting argument, because why do I need to change my frame shape based on my brake time? I mean, I really don't need to. I mean, if I really think about designing a really efficient frame, I can completely integrate and hide my brake with the exact same frame shape arguably the frame shape and the fork and how you have to have these bolts and these things that stick on. I don't know how it would be faster. Doesn't make sense to me.
Well, for marketing, it has to be, right. So every year the
Sure.
frame shape, it's got to be 2 to 4% more aero, right? And given that,
Yep.
like, from when I started triathlon 15 years ago, I should be on a bike that has 0 drag.
Yep.
If it's 2 to 4% all the time, it's going to
Mhm.
eventually be nothing. But so I actually contend that a really good aero frame from 5 years ago, that is a rim brake bike, is faster than a brand new.
Yep.
Yeah. Okay. Good.
I wouldn't disagree.
Well, but it does influence your tire width and wheel width choice that you can go.
You can only go so wide. Like I can only go to a 28.
Right.
I can only go to the 28 is the maximum tire width.
Yep.
But that's fine. 28 to me seems like optimal anyways.
Yeah.
What's really interesting, and this is something that like I came out of the wind tunnel last time I was there when we were looking at wheels, and I had to go back to the numbers like 3 times because I didn't believe it. But our gravel wheel, which uses a 32 mil road tire because it's the smallest you can put on it from a safety perspective, with a disc brake, because that's the only thing you do with gravel is disc, is 55 millimeters deep. Our road wheel, which is 77 millimeters deep, narrower because of bike geometry, with a 28 mil tire, which is the fastest, is slower than that gravel wheel at 55 millimeters.
Mm.
And I like triple checked. I'm like, there's no way. There's a wrong number. I even like went back to the original data and looked at it. And again, it goes right back to what I say is that the aerodynamics is a combination of width and depth, right? When you can do things that are wider, if you think of like an airplane wing and the old, like they're called NACA profiles, people used to say that like an old toroidal rim or even like the old V-shaped rims, it was like a NACA profile. NACA profiles are super broad and blunt, and they don't look anything like a tire on an old rim. But what we're getting with these super wide rims and wider tires is it's starting to resemble something more similar to an NACA profile. And I can tell you that the number of hours and wind tunnel time that has gone into things like designing an airplane wing is a lot more than people
Yeah.
put into cycling.
Oh,
So if they made skinny shapes and they were better for airplane wings, they would come up with ways to reinforce them to be strong, but they don't do that. So that's this combination of width and depth.
so I have this question for you then. So you know me, like I don't buy new stuff. I got old stuff. And what if I have an old rim that's more optimized for, let's say, a 25, right?
Yeah.
And I put a 30 on it, a 30 mil tire. Would it be faster in general?
No.
I should go
Your
with
rolling resistance, well, it goes right back to the combination of rolling resistance and aerodynamics, right? So rolling resistance wise, you're going to test that and it's going to look faster.
Yeah.
The minute you put that in a wind tunnel, you're going to lose it. So when I talk about the like rule of 105, that's why it's still relevant, but it needs to have some give. When you go from when you go that much, you've gone over. I call them like ice cream cones.
Yeah, exactly.
It's like an ice cream cone setup, right? So you've got the sidewall, the rim, and the brake track, and then you put this tire on. It looks like an ice cream cone if you were to section it. When you get into like an ice cream cone shape, you might as well just throw it away. I mean, you that's why you drop down to a narrower tire, is because you do need to consider the aerodynamics. If they're not both considered, you've lost half the equation.
Yeah, and so it's funny because I do a 25 because I have an older rim that's optimized
Yeah.
for 25. So I do 25s, and people are like, "Oh, you should be on 28s." I'm like, "Yeah, well, should I?" I know this wheel is optimized for this width, and I can still
Yep.
run. I don't weigh that much. I can still run it at 80, 85 psi.
Yeah.
I'm fine. So I'm doing the right thing.
Yep. Totally.
I want
How
to.
narrow is your rim?
It's all I know. When I looked at it, it said it was optimized for a 25. I can't remember the internal.
And then go with that.
Maybe it's a 19 mil internal. Does that sound about right?
Yeah, that's 25.
Yeah, yeah. And so I was like, okay, well, I'm sticking with that, even though everyone's telling me, oh, you should be on 28s or 30s. I'm like, no, I shouldn't, because that's not what I have.
Nope.
All right, let me get another question here because Ted brought it up, the disc wheel, and I'm pretty sure we all align with this.
Number 4, you're gonna give away? we always talk about disc wheels.
Oh, yeah. No, I know this is one of your favorite ones. So people will always ask, I'm doing this course, whatever this course is. Should I ride my disc wheel?
Yes.
It's easy, right? Yes. Full
If
stop.
it's legal, yes. So let me go a little further on that though. There's two reasons people say they don't want to use a disc. Generally, it's because they think it's too heavy, right? Because it's a hilly course. Even if you're looking at Savage Man, which is the most vertical any like Ironman in North America, I think maybe of the world, there's no such thing as a hilly course in Ironman, or that don't exist. We've studied this where you look at super heavy wheels with aerodynamics versus theoretically light sets of wheels. The aero win every time on the hilliest course you can imagine. So ignore that one. The second thing people talk about is, am I going to be able to handle this? Actually, a disc wheel helps stabilize the bike because it's in the rear, it's fixed in the frame, there's no steering axis, and it moves something called the center of pressure to the rear of the bike, taking emphasis off the front wheel. So ride it. unless it's illegal, like Cozumel or Kona,
Mhm.
it's because the wind literally does blow across the side of the road and you will get pushed. Ride your disc wheel.
Mhm.
So
Always.
can I add one little thing to that? And so this is a question that I had somebody ask me who I'm working with, and they're a relatively slower rider. So maybe average speed is 17 miles an hour, right? At
Mhm.
what point is the disc wheel like where it maybe doesn't help you as much because you're not going fast enough? Is that a thing?
Myth.
Okay,
Myth.
that's
It's
exactly what I
this
thought.
whole thing. You're exactly right. There's been this myth forever that you need to be going 20 miles is one I hear all the time, or 19 miles an hour for aerodynamics to matter. That's just not true. I think it was formulated and created from, if people look at the drag equation, where drag is how you calculate your aerodynamic drag. There's a velocity component in there that is squared, it's your relative velocity. And so if you graph drag is velocity, relative velocity increases, it goes up exponentially. It's got like a curve. And so people would look at that and say, well, lower, it doesn't matter. The truth is that the slower you go, the more time you save over a course.
Exactly.
So, right. And this is what people, every time I say this, people are like, you got to think about it for a minute. But I've done the math on this in multiple blogs that I've written and have shown this, that if you think about being on the course for 4 hours, or 4.5 hours for a smoking bike time, which pros are doing now these days, they're only on the course for that amount of time, so they can only experience savings in that time window. So that time savings gets truncated because they are only on the course for a certain number of minutes. If you're going out and doing an 8-hour, Ironman bike time, then you have all of this time that you can experience savings in, right? So of the percentage of minutes that you can shave off, it's greater than the 4-hour cyclist. So you're saving more time the slower you go because you're experiencing the savings, the aerodynamic benefit for a longer period of time.
I love that. And the other thing I was telling them, like, okay, let's say you're going 10 miles an hour into a 20-mile-an-hour headwind. Now
Yep.
30-mile-an-hour resultant, and that becomes very important. And trust me, you're going to want that 10 watts.
Well, and that's what people think. People say this all the time is they say, well, I only go this fast. I'm like, but aerodynamics doesn't care about that.
Mhm.
It doesn't care how fast you go. It cares about the relative velocity, and you can't control that.
You cannot control that at all.
Right?
That's great.
No, you can't. No, not at all.
Well, I love this, and I love talking the equation and the mechanics, and this is wonderful. You're always so generous with your time. It's great to have you on. I just saw one of your product videos though, and your mini pump is one of your best new sellers now. Is that in terms of
Yeah.
product?
Yeah, people are loving the mini pump and that. And the other thing people are loving is the CO2 regulator. It's this really cool, like little regulator that it's got a dial. I don't know, it's just people keep buying the pumps and the regulator. So go for it.
Love
Awesome.
it.
Awesome. All right. Well, hey, thank you so much, John, for your time. We
Yeah.
really, honestly, I think this might be your second or third time you've come on, and we've been on
Yeah.
your podcast a couple times, and we got a great time. Always, we have great conversations with you. It's always so nice, and because he's Canadian and I'm Canadian, we always get along.
That's right.
We always get along well. But we appreciate you, and we
Yeah.
appreciate you being a big part of the cycling community in Las Vegas. And you know, I correct me if I'm wrong. The only cycling wheel company in Las Vegas that we know of.
Yeah, I think so. There was one a couple of years ago that I don't think they are still around.
Mhm.
Okay,
But yeah, we're the only guys here. So
so
good.
yeah, awesome stuff, and we really do appreciate you.
Yeah.
So thank you.
Thanks, John.
Excellent. Well, thank you guys. Appreciate you always having me on. It's always good times.
We'll get you on again because I know we're just scratching the surface here with all these things. So this is great. All right, have a great
All
weekend.
right. You too.